Okay, this is problem 23.8. It's on page 623. So you can read that problem. Now to solve this problem, first I'm going to draw a diagram of the two plates. So here's my parallel plates, and there's a distance d between them. That d I know is 4 millimeters. I also know that there is a potential difference between the two plates of 110 volts. To solve this problem, I'm going to use the fundamental relationship, which is delta V equals minus E dot delta R. Okay. Now to use this relationship, you have to find you have to define a delta R vector that's going to be useful for the problem. You can choose its direction and its length, its magnitude, but you want to pick one, that's sensible for the problem. Now, in this case, the sensible choice would be from one end of the plate directly to the other. Okay? So that's my delta R vector. And you can see immediately that, for example, the magnitude of delta R is going to be D. Now the next thing you need to know is the direction of the electric field, because you're going to have to figure out remember that this inner product involves a cosine, so you need the angle between these two vectors. Now I don't tell you the direction, or the problem doesn't tell you the direction of the electric field, but if you look back at page 611, figure 23.6, it shows that the electric field in parallel plates are directed perpendicular to the plates between from one plate to the other. Okay, so, and I don't know which of these plates is positive and negative, but it doesn't ask me for the direction, just the magnitude. So I can just assume that it's going. I pick things so that it's going in the same direction. That makes it real easy now because the theta angle is 0. And this relationship here is just going to be now minus E times D. Now you see the only unknown here is E, which is what we've asked for. What we're going to ask for. We have delta V and D. So now that I have all these values, I can just plug this stuff in. And again, since I'm just interested in the magnitude, that will turn into this. I'll put an absolute value sign there. So it's just 110 volts divided by the 4 millimeters. And that, I'll let you confirm, is 28 kilovolts per meter. The next problem we're going to do is 23.55, and this is on page 625. I'll let you read that problem. Now in this one there's no real geometry given us, like parallel plates or anything, but it's asking about a potential difference. So to think about it, what I'm going to do is I'm going to draw some equipotential surfaces. And I'm going to draw an initial and a final position for my proton. Now its initial velocity, I don't really know what direction its initial or final velocity is, but I can draw them there. It's obviously speeding up because this potential difference is giving it some kinetic energy, right? And I have a potential difference here, let's say of delta V. And again, I don't know what the path is, but it's some path here. Well, let's see what we're given here. We're given the change in kinetic energy. This delta K is 125 keV, that's kilo electron volts. And we're also given the charge on the particle, which is 3.2 times 10 to the minus 19 coulombs. Now, if you look at what the value of E is, that's the fundamental unit of charge, that's 1.6 times 10 to the minus 19. So Q is actually equal to 2 times E. And if you think about it, that's right, because a helium nucleus is 2 protons and 2 neutrons, so it's got a charge of plus 2 in terms of fundamental units, right? Plus 2 times the charge on the proton, which is E. Now this is useful to express charges in terms of E if you're given, energy in terms of electron volts. We'll see that when I solve the problem at the end. Okay, so this is a conservation of energy problem because there are no external forces on the proton. That means I can write out the conservation of energy. Delta E should be equal to 0, and the change in energy is going to be the change in electric potential energy, which we know is going to be Q delta V, plus the change in kinetic energy. That's the general formula. Now in this specific case, let me fill some of that in. The Q here is 2E, and we've got delta V plus delta K. This equation, by the way, right here is right from the earlier lecture that I posted. Alright, well, this is actually pretty easy because the only unknown in this is delta V. We have delta K is given to us, and we know the electric charge, so let's just solve. That can be solved pretty easily. I won't insult you by going through all the steps, but you can verify that this delta V should be minus delta K over 2E. Okay, so we'll work that out. Filling in what we know what delta K is, the energy we wanted to add was 1.25 times 10 to the 5 electron volts, and we divide that by 2E. Now, this may seem a little bit more complicated than it is because you'd think we need to stick in the value of E, which is 1.6 times 10 to the minus 19 coulombs. However, the unit of energy here is electron volt, which is 1.6 times 10 to the minus 19 joules. So those terms will cancel. Symbolically, it's the same as canceling this E with this E. So the final answer in all its simplicity is delta V equals minus, and I'll let you verify that I have the units correctly there, 63 kilovolts. Now you'll notice I got a minus sign here. Is that correct? Is that sensible? Let's go back and look at my diagram, the way I've defined my directions. I define my directions as going from an initial point here to this point here, so that the delta V is the potential here minus this. Since it's negative, that implies that the potential on this surface is less than this surface, right? And that implies, for example, that the electric field points to the right, and that makes sense because the particle is actually moving to the right, so it's going to speed up, right? So if the displacement is in the general direction of the force, of the electric force on it, since it is positive, the electric force will be in the direction of the electric field, the work will be positive, and it will speed up if this potential here is less than that potential. So in fact, that sign does in fact make sense.